So I'm pleased to introduce today's CAM speaker, Yisong Yang from NYU. So he is one of the student-nominated speakers. So in the fall semester, we mostly took student suggestions for our CAM Colloquium speakers. And Yisong was one of the recommendations from Lily, who spoke very highly of him as a professor. Unfortunately, we overbooked the fall, so Yisong was gracious enough to allow us to move his slot to the spring semester. So I'm grateful that he's able to come in and speak to us today. So Yisong's area is mathematical physics, and you can probably tell that from the title and abstract of the talk that he sent. He's been centered at NYU, or centered in New York at least, for some time. Is currently in the professor in the math department at Cornell, has a number of honors, is a fellow of the American Math Society, a member of the London Math Society, very, very well published, has a textbook that is mentioned in the abstract, which quickly went on to my Amazon wish list, as happens with all books that sound interesting that come across my way. So today, he's going to be talking to us about an interesting topic involving some nonlinear PDEs and some mathematical physics, as is one. And with that, I'll let Professor Yang take it away.
Thank you very much, David, for your kind introduction for me. And also thank you, Lily, for your recommendation of my talk here. Thank you very much. I'm honored to give a talk at Cornell University Applied Math Center. Today, I will talk about nonlinear electrodynamics, and also it is applications to some issues in theoretical physics. Today, we had a lunchtime meeting with a few of you students, and then questions arise about nonlinear structure of electrodynamics. So this kind of chat motivated me to rename our talk with a short title. Let me write down. Thus, I like to share this kind of emotion about our study today. I would call it I don't know how to write well. The wonders or the wonders of and the inside insights by nonlinearity. Okay, this is what I like to emphasize here today. Let's go to the talk. Okay. Okay, I have to disable this. Okay. Okay. First, we are going to start with a discussion of the puzzle, the great puzzle of electron as a point particle. We all know that the structure of an electron is a big puzzle for physicists. Okay, electron has no material structure, and also the electron would possess the basic unit of the electric charge. In fact, in terms of QED, you can have a quantum mechanical description, but in terms of classical physics or classical mechanics, the model of electron has been a puzzle. For example, in the year of '62, Dirac wrote a paper about an extensible model of the electron, where he modeled the electron by a spherical surface of this shape. like a surface, okay? The charge would be extended over the surface of the sphere. But the most popular model for the electron would be electron is viewed as a point charge. This kind of model is the most popular model of electron. But if you take this kind of model, you run into trouble immediately because the electric charge of a point particle would follow the Coulomb's law. The electric field would be proportional to the reciprocal of the square of the radius. And then you plug it into your energy density here, you integrate, you're going to have infinity for the energy, okay? So this is the big puzzle of electron modeled by a point charge, okay? Likewise, if you model a magnetic charge as a point particle, you have the same divergence problem. So in this way, a finite point charge, either electric or magnetic, are both excluded in the theory of Maxwell theory. Let's now look at like a comparison, okay? Supposedly, if you model the electron by a ball, so that the ball has a constant charge density, and you try to fill in this ball from infinity to a finite sphere, then you count the total work to be done by the Coulomb force, okay? And then you're going to show that for this solid charge, your energy will be given by this famous formula, 3/5 times the charge squared over the radius squared, okay? If you do so, and then you realize the rest energy of the electron by the MC squared calculation, you put in there, and then you put electron charge there, you can estimate the radius of the electron to be 10 to the negative 13 powers of centimeter. This number here is too big because, as we know, the proton has a radius of like same size, okay? So therefore the electron has an estimate of being too large. So therefore, classically, electron should be much smaller, okay? Like a point charge, for example, okay? Now, look at now the Born-Infeld theory. This theory was published in year 33 and 34 last century in 4 papers, 2 papers in Nature, 2 papers in the Proceedings of the Royal Society, okay? And their conclusion is a point electric charge will carry a finite energy by their theory, okay? The theory is quite old, but in recent years, the theory is being revived due to its interest in contemporary theoretical physics, especially in string theory, gravitation, and cosmology. Today, we're going to get into the subjects of gravitation, cosmology, and particle physics, okay? Quickly, okay. The PDEs and or mathematical challenges would be PDEs and ODEs of highly nonlinear structures, okay? And the area provides a lot of opportunities in sense of fundamental physics and profound mathematics, okay? So I view this as a perfect frontier area for mathematical physics. Let's now see what this is, okay? This is a picture of Born and Enfield. Born was a German physicist, and in fact, he was trained as a mathematician. In fact, a few people know his advisor. What was the name of his advisor? His advisor is this favorite people pair we know, Ranji Kutta. David knows Ranji Kutta. In fact, Ranji was his advisor. So therefore, Born was trained as a mathematician, in fact, okay? And Enfield was a Polish physicist, okay? So today we're going to touch 4 areas. First is, what is Born-Infeld theory, okay? And then second is I'm going to use the Born-Infeld theory to tackle a problem called the monopole problem. Okay, I would like to argue that monopole will not exist in the context of Born-Infeld theory. Okay, and then I like to touch the area of regular black holes with electric charge, electric or magnetic charge. And eventually we're going to touch something about cosmology if we have time, okay? Now, every time I have to disable the, okay. Let's now look at the motivation of the Born-Infeld theory, okay? First, for a free particle in motion of mass m, then you know the Newton Lagrangian action would be the kinetic energy, right? This one, if you make this relativistic, make it into relativistic mechanics, then by Einstein's theory of special relativity, your Lagrangian has to be revised into the Einstein Lagrangian action function. Okay, c here is the speed of light. Okay, so therefore you immediately encounter a nonlinear extension of the Newton mechanics into this kind of Einstein action. Okay, and you see clearly that the interaction here would introduce a cutoff or upper bound for your velocity. The velocity has to be below the velocity of light, okay? And moreover, if you take the low velocity limit, you make Taylor expansion, then your Newton action would be recovered, okay? Or if your C here is taken to be infinity or B taken to be infinity, you take the limit. The limiting situation would give you Newton action there, okay? So therefore, from this, Newton mechanics is a limiting case of Einstein mechanics, Einstein's special relativity. And moreover, Einstein relativity theory is a nonlinear theory. It's a nonlinear extension of the Newton theory, okay? You put Newton action under the radical root, okay? So then the motivation of the Born-Infeld is they take the Maxwell interaction there, okay, and this one you are going to have trouble to accommodate electric charge, point charge, and then they say why not? Okay, we are going to mimic what Einstein did to revise the action density here into the following one with a radical root there, okay, so that you replace the Maxwell interaction under a radical root with a parameter b here. B can be very large, okay? And then in the large b limit or weak field limit, you're going to recover the Maxwell interaction, okay? Then the theory becomes linear and so on and so forth, okay? So this is the Born-Infeld theory. It is quite natural and quite simple, in fact, follow the idea of Einstein about special relativity, okay? And from here, Born-Infeld argued that, okay, so this will introduce a cutoff bound for the electric field. Electric field, because if you really take now the B here, magnetic field to be 0, the electric field here would appear with a negative sign in front. So therefore, the B would be an upper bound for the electric field, okay? So therefore, in terms of the Born-Infeld theory, the electric field will be bounded by a large quantity B, okay? So in this way, it is helpful to overcome this divergence problem for electric point charge, okay, right? Okay, so from here, if you take equation of motion of this Lagrangian action here, you're going to get the equation of motion. This equation of motion are called the Born-Infeld equations. They take the same form of Maxwell equation form when the D is viewed as the displacement field, and the H there is viewed as intensity magnetic field, okay? in the Maxwell theory, they are going to be related linearly by the electric magnetic coefficients, right? The epsilon here is called permittivity, and the mu here is called permeability, right? But in the Born-Infeld theory, epsilon and the mu would be the field dependent, okay? So therefore, now we can see that the Born-Infeld theory, it is a nonlinear theory of electrodynamics, where your constant epsilon mu becomes functional dependent, okay? Which means that the electric and magnetic field would interact, would couple with the media, basically. So therefore, we say that Maxwell theory here now extended into a nonlinear theory of Born-Infeld, so that your media becomes nonlinear, okay? So this is the Born-Infeld equations and Born-Infeld theory. Let's now look at the consequences of this theory, okay? First, the Pdes, okay? Supposedly, if you take your electric field to be given by a scalar potential and the magnetic field to be given by a vector potential, and then if you look at the static case, then you have no time dependence, your equation would look like a coupled system of equations. First one is divergence equation. Second one is the curl equation, okay? And the phi and A are coupled together, okay? Now this is already very, very new, okay? Almost no work is done for this coupled system of equations, okay? In the special case, when you talk about a purely electric or purely magnetic case, okay, then the two equations becomes decoupled. This equation, the scalar equation, the other one is the vector equation, okay? The scalar equation arises in differential geometry a lot, okay? This was studied by the work of Cheng and Yao. This was a long time ago, okay? By these two people. Basically, they showed that the equation, the scalar equation, has something called the Liouville-Bernstein property, which means the most general solution to the scalar equation there would be a linear function of phi, okay? This is their work. But for the vector field equation, no one has studied much yet. Okay, very few study has been done for this vector equation there, magnetic equation there, okay? But you can still consider to convert this vector equation into a scalar equation, so that the two equations can become two divergence equations of scalar form, so that you can rewrite the whole thing as by an action principle. Okay, you can show that the action principle here will give you this coupled equation, the electric magnetic coupled equations. Okay, this coupled equation here, anything about it would be interesting. For example, what would be the Bernstein-Liouville property of this coupled system of equations? Or the question is, what would be the most general solution to this coupled equations? Okay, all these are not well done yet. Okay, so much for the PDEs. Now we're going to study the resolution of the point charge electric puzzle, this problem. Okay, now suppose now you look at a point charge. For a point charge, your displacement would be given by the delta function, like this one, and your magnetic field will be 0. Okay. In this case, you can solve this equation so that your electric displacement field would follow the Coulomb's law. Okay, radial direction would be like that. Okay, and then remember you can solve for E in your nonlinear relation, like this one. Solve for E in this nonlinear relation, this one. You convert the E, you get your expression for E explicitly. This was done by Born and Enfield. You plug in your D into it, and then you see that your electric field here now is really bounded. It's globally bounded by the parameter B. Very good. Another one is if you take a large R limit, okay, and then in the large R limit of this result, you see that your leading term would be Coulomb. It would be Coulomb's law. Okay. Or if you take a large B limit, you also get Coulomb's law. Okay. So therefore, you see that the Maxwell theory is well recovered in terms of the electric field. All right. Now let us now compute what the energy is. Is the energy really finite with this? Okay. To compute the energy, we are going to now look at what the energy density or the Hamiltonian look like in the Born-Infeld theory. It is given by this complex, complicated expression. Okay. From here, if you take a large B limit, you recover the Maxwell energy density. Okay. No surprising here. No surprise here. Okay. If you insert what your solution E is into your Hamiltonian and compute this energy, you see that energy is really finite and given explicitly by this number there, so that you have a quantity in front, which is universal, and then you have a Q squared there, and with the A in the denominator. The A here has the unit of length. Okay, it is very it's comparable to what we did before. It was like 3/5. Remember, for a solid electric solid, it was like a Q squared over R. We did this calculation before. So this result here for the Born-Infeld theory is comparable to what we did before, so that the little q here plays the role of the large q, and A plays the role of the radius R, and then the universal constant here plays the role of 3/5. Okay, so it is quite comparable. So therefore, we like to view the A here as our new radius of electron. But the thing is, because our electric field here is a continuous field, not a point like a concentration there. So therefore, your electron here is not a point particle in terms of the E field, but it is a point particle in terms of the D field. The electric displacement field is point particle, but in terms of the measurable electric field, it is going to be an extended thing, okay, not a point particle. So let's now compute our electric charge. Electric charge is going to be computed by the electric field by taking divergence, okay? And then you show that the charge density is going to be given by Q, and then this R here appear in the denominator here, okay? It is quite interesting because you see that when R goes to 0, the charge would go to infinity as fast as 1/R, okay? So you still have this energy density blow up. It is highly, highly concentrated near the point charge R equal to 0. And but the charge density would go to 0 quickly, like 1/R to the power 7, okay? So therefore the decay is quite fast, okay? So therefore it will give you a highly concentrated profile for the free electric charge in this situation in terms of electric field E, okay? This is the measurable electric field E, okay? So if you plot the structure here, you're going to see this density here. It decays fast near when R equals A, you get this kind of a big concentration here in this area here, but decays to 0 fast when R is bigger than A, basically. Okay. From here, you can estimate the radius of the electric charge or the electron. Okay. If you insert all the electron data, you're going to get this A here. A is still in this power 10 to the negative 13 power centimeter, but 2.28. This number is even bigger than what our estimate was before, okay? But this is not a troublesome result, because here our density distribution is continuous, okay? It's not like a solid distribution, not like this, okay? It's not a physical solid, but this is like more like the electric charge more is like a cloud rather than a solid, okay? So this is the picture I got from online, okay? You can see this kind of cloud in sky, so that the high concentration of the of the cloud is in the center, but from far away you see it. It's like a cloud. It's like a bigger sized ball. Okay. So the electric charge or electron may have this kind of appearance physically or classically in our calculation. So this is now like a quick summary that electron has two appearances. Okay. One is if you view an electron appear in terms of the electric displacement density, displacement field, it looks like a point charge. But in terms of electric field, the appearance is like a cloud, like a spherical cloud. Okay. So this is a Born-Infeld work. But if you really compute the total electric charge in terms of Q, you get the same thing. So which means if you compute the total charge in the whole space, the concentration would give you the same reading of the prescribed point charge Q. Okay, so the free charge and the electric charge, they agree in fact. Okay, no problem. Okay, so this is the introduction to the Born-Infeld theory. But now we go quickly to the monopole problem. What is the monopole problem? Monopole problem is if you view same thing, if you look at a magnetic field given as a point charge, okay, and then you're going to encounter this question of whether such a point particle of magnetic charge would exist. Okay, in fact, the magnetic charge point charge is called a monopole. Monopole was proposed by Dirac a long time ago. And this idea here has fascinated a lot of physicists and mathematicians as well, because it will give us an interpretation why electric charges they all have a minimum unit charge. So why they all would be computed by a unit basic unit, like multiples of electric charge of electron, for example. Okay. So people are still pursuing this research experiment to try to find out whether magnetic monopoles would really exist. Okay, there was a few papers. One paper is like in 2014 by Elizabeth Gibney. She used like condensed matter simulation to give us a picture of magnetic monopole. But magnetic monopole as a particle has never been discovered in nature yet. So therefore, the question would arise, our first question would arise, okay, can the Born-Infeld theory offer some kind of insight so that we can use some kind of insight or mechanism to reject monopole? Okay, but this is cannot be done in the Born-Infeld theory, because Born-Infeld theory, if you pursue the same thing, the Born-Infeld theory would allow magnetic monopole of finite charge. So there's no way to exclude a magnetic monopole at all. Okay. So therefore, our question here is quite like something beyond Born-Infeld theory. In the context of the Born-Infeld theory, are we able to exclude magnetic monopole? Okay, so this is our question here. Okay, so let's go quickly. So here we like to consider generalized Born-Infeld theory so that our interaction here would follow a general function of Fs. S here is Maxwell, okay, and Fs is a general function, okay, so that to recover Maxwell theory, you like to have F0 to be 0 and the derivative of F at 0 would be 1. Okay, for example, when Fs is equal to S, you recover the Maxwell theory, okay? And then when Fs is given by this radical function there, you recover the Born-Infeld theory, okay? So here is our answer. You can make an extension of the Born-Infeld theory in this fashion here. When the F here is suitable, you could recover the Maxwell theory, and at the same time, you can show that monopoles will not exist. Okay, so how would we do this? Okay, we have to make our function here very, very general. Okay, how general? Okay, let's now review this kind of a celebrated Stonewall theorem. It says any nonlinear function here, any function here, can be approximated by polynomials, right? Polynomials are going to be dense in functions of with continuity, for example. Okay, so therefore, let's now consider our nonlinear functions to be given by a polynomial. Okay, for a polynomial of this type, you can show that, of course, there's no cutoff. Okay, because you have no radical root anymore. No cutoff for electric field. Okay, and then you can show that in this case, you go through all this nonlinear theory of Born-Infeld. You can show, as before, finite energy electric charges are going to be accommodated, no problem, okay? But magnetic monopoles are not going to be accommodated because they will carry infinite energy, okay? Why? Because the appearance of your, how this nonlinear relations are related, okay? This kind of relation, how this kind of constitutive equations are going to appear. You can show this kind of details, okay? So this is quite encouraging that you can have a nonlinear theory with polynomial type, in fact, any polynomial type nonlinearity, okay? So that you can accommodate finite energy electric charge, but at the same time, all monopoles are going to be excluded because of divergence of energy, okay? So therefore now you see an isometry of electromagnetism, okay, in the generically given nonlinear interactions, okay? So therefore, this is like a progress we see here. The second topic I'm going to go to is about the black hole and the singularity problem, okay? It is quite amazing that last year's Nobel Prize was given by Penrose for his work on black holes, okay? In fact, some time ago, in the year '88, Hawken and Penrose was awarded the World Prize in physics for their work on singularity theory, okay? Singularity theory is a more profound theory for than the monopole, than the black hole theory. Okay, so let us now look at now what can be used in the context of the Born-Infeld theory to make some progress or understanding of the singularity theorem of Penrose and Hawken. Okay, to see this, let's now review something about black hole. Okay. Black hole of mass m is given by this one, the singular metric. Okay, singular metric would have black hole when this factor there becomes 0. Okay, that will give you coordinate singularity, but the coordinate singularity is not a real singularity because if you use suitable change of coordinates, you can eliminate those singularities. Okay. In fact, if you look at now the scalar curvature, for example, the Kirchmann curvature here, this invariant K here, you can show that the singularity Rs here will not appear at all, but only would appear when R equal to 0. Okay. The singularity would happen at the center of the space-time, not at the horizon, not at the R equals to Rs, okay? R equals to Rs is not a singularity, but R equal to 0 is, okay? This is our singularity thing. Now, let us now look at now what happens, what kind of consequence a singularity would give you. So here is like a popular science statement of what a singularity would be look like physically. Singularity is where the curvature becomes infinite, or the density of matter becomes infinite, or the space-time will no longer be a manifold. Okay, basically, this is where mathematics would fail, or mathematics fail means what? Your physical law would also fail. Okay, So therefore, with singularity, you see, because singularity must exist in general, then you see, oh, there are some spots in space-time. There's no physical theory. Physical theory will not operate there. Okay, so this is also called incompleteness of physical universe. Okay, basically, this is what singularity would mean for us. Okay, it caused by a black hole. Okay, black hole is not essential, but singularity, yes. Okay, mathematical wise. Okay, so let us now talk about black hole metric again. Black hole metric will look like this A factor or the metric factor. Okay, this is something we encounter when r equal to 0, you get singularity. Okay, but if you consider black hole with electric or magnetic charge, you introduce into your calculation of the Einstein equation, you're going to show that your metric factor will be modified into this following one. Okay, in the following one, the metric there is the famous Reissner-Nordstrom black hole metric. And you see that you have this worsened singularity here. Before it was 1 over r type. Now you have what 1 over r squared type. Okay, this singularity is considered worse if you compute your curvature, your k curvature, your scalar curvature. You see that this 1 over 8 would appear here. Okay, it is going to be worse than before. It was used to be like 1 over 6 type, right? 1 over 6 type. Okay, now this is 1 over 8 type because of the presence of electric and magnetic charges. Okay, so therefore you have this singularity order here is higher. Okay, now the question would arise now, because this was based on the Maxwell theory. Okay, now with revised Born-Infeld theory, are we going to reduce our singularity if we have finite energy? Okay, so I use this term here, relegate. Okay, well, the Born-Infeld theory relegate or lessen the curvature singularity due to finite energy. Okay, this is the second question here we like to answer here. The answer is yes. With Born-Infeld theory, you really are able to relegate or lessen your curvature singularity. Okay, or sometimes even remove it. Okay, let's see how we do it. Okay, so here is your Einstein equation. Try to solve this equation. I'll go through this quickly. The equation would lead to this metric tensor to be calculated. Okay, and then from here, you'll have this expression so that the m here is a mass and the E here is the energy of the electric magnetic sector. Okay, so the tail term comes from the Hamiltonian or energy density of the electric magnetic part. Okay, so from this expression, you see quickly that your singularity here is not worsened. It's not like here, not like what we have here for this. You have this r square here to appear, because there you have divergent electric magnetic energy. Now we have convergent one, so that you see clearly that your singular part is not worsened. It's same level. Okay, because when E here is finite, you have same level of singularity. Okay, so therefore, the Born-Infeld theory is really useful to relegate or lessen your singularity due to electric charge and magnetic charge. Okay. Moreover, from this expression, you see clearly you can even reduce it. Okay. So what happens? Question here: what happens if E and M are equal? If E and M are equal, then your singularity can be reduced, right? The term there would disappear, okay? And then the term here would be important. So in this way, you're hopeful to get some regularized black hole, okay? Your curvature singularity may be eliminated in this case. So indeed, this is the case, okay? So if you consider this a critical mass energy condition, okay? And then you can show that our metric factor becomes this nicer one, so that everything here, the singularity would be contained in this last tail term there, okay? So therefore, you can make your electromagnetic theory suitable so that you are able to remove even your singular point or curvature singularity. It is hopeful, okay? In fact, some recent examples are thus, examples, for example, the Born-Infeld black hole or Hayward black hole, and also something called exponential black hole. Okay, so what is a Born-Infeld black hole? Born-Infeld black hole is really regular. It's this kind of type. Okay, so 1/r squared type is not there anymore. It's regular. Okay, you have no more curvature singularity for this problem. Okay. It is nice. This is regular, no singular point, singularity free. Okay, free of singular point of singularity. Okay, I'll do this. But the Born-Infeld black hole here is quite mysterious for a long time. Okay, the Born-Infeld black hole was introduced a long time ago. The same time when Penrose Hawkins published their singularity theorem, same time, about the same time. But Born-Infeld black hole was considered as an approximation solution, okay, to the Einstein equation. No one knows where it comes from, okay, and he did not explain how he get his black hole metric, okay. In 98, okay, some people published a work. They derived the Born-Infeld monopole, the Born-Infeld black hole by the theory of generalized Born-Infeld theory when they take this very strange form of the nonlinear function, okay, fs, given by this kind of rational form with all this kind of radical root and this kind of appearance, okay. And then they show with this kind of Born-Infeld theory, you develop your electric or magnetic charged black hole, get into this kind of Born-Infeld monopole, Born-Infeld black hole metric. Okay, so therefore this is quite a progress. It was considered quite a progress. Okay, later on, a physicist called Hayward, okay, derived another more regular black hole with this metric factor. Okay. And his work was also based on Born-Infeld theory, like this type. Okay, it also involves radical root of this kind of structure. Okay, which is quite a very strange structure, in fact. Okay, the common feature of those two structures would be you have to consider radical root under it, negative s and some radical root. S is given by the Maxwell theory here, so that you see that if you take a magnetic field to be 0, but to consider electric field only, you get negative in under the radical sign, you run into trouble, so that your electromagnetic theory is incomplete because the theory will not accommodate electric field, right? Because when your magnetic field becomes 0, your S becomes positive and the negative S becomes negative. The whole thing here would ruin your theory as a complete electromagnetic theory. Okay, so the Born-Infeld and the Hayward black hole models, if you look at the Born-Infeld Lagrangian, the Lagrangian will not give you a full electromagnetic theory, which is a drawback, in fact. Okay. So let's now look at our theory that we are in search of a complete electromagnetic theory that will offer us regular black hole solutions. Okay, how would we do that? Okay, so we do this. We take the binomial model, okay, of this form. Okay, S here is our S here, the same thing, the Maxwell interaction there. Okay, but this is nonlinear theory, right? Okay, n here is integer, so everything here is accommodated, no problem to accommodate any s here. S has no sign restriction at all, okay? Now, the theory we know will not accommodate, because this is a polynomial, right? It will not accommodate magnetic charge, but only electric charge, okay? It is an electromagnetic theory, but will not accept point magnetic charge, okay? For this problem, we're not working on this one, but we're working on the limit of this. Take n equal to infinity limit. Then what you get is the limit becomes exponential, okay? In the exponential case, the S here has no restriction, no cutoff, okay? And then you can show that this model here would allow both electric and magnetic point charges of finite energy, and also it will be nice enough to make your black hole of regular type, okay? So the metric tensor becomes this one, because if you take your Hamiltonian becomes negative in the power here in the exponential, okay? So therefore the function here is quite nice, right? There's something we call the modifier function. Modifier function means the function here would be smooth at rho equal to 0, right? Because the negative in the power here would make the whole thing vanish as fast as anything of this order there, okay? So therefore the part here would give you a nice contribution, so that you see that you have this power type contribution here to make the whole thing regular, okay? So let's now compute your curvature here. Your curvature here becomes, K becomes no more singularity, no R here in the denominator anymore, nothing like that, okay? You would have a constant part here when R near 0, and also a power type here, okay? So therefore, the curvature singularity is being removed, in fact, okay? At the same time, we have the full theory of electromagnetism, okay? So this is considered a progress of the subject, okay? Now let's go to the third topic of the applications, okay? We're going to consider cosmology, okay? Cosmology is based on the Hilbert-Einstein action. You have the Ricci scalar here as first term, and then you have this matter Lagrangian as second term, and then you look at your equation of motion, or the Euler-Lagrange equation of this Einstein-Hilbert action. Then you talk about a time-dependent problem. Then you look at now how the solution would look like in terms of t, and then this will give you a cosmological evolution. Okay. Now the easiest situation would be called an isotropic and homogeneous situation, so that everything here would be spatial independent, but only time dependent. Okay. This is a large scale scenario for the universe. Okay, you have a isotropic and homogeneous universe. So therefore, your metric tensor would become this one with only 1 degree of freedom. 1 degree of freedom means what? You have a scale factor in front, which is unknown. The rest, the form is given. Okay, so this is the famous Robertson-Walker space-time line element, and you plug everything back into the equation and then solve for solutions and then make predictions of the universe. Okay. So here is our picture of cosmology. Okay, cosmology says by the current observation, by the data we know, the scale factor AT would follow the picture here. At time 0, the AT would be equal to 0. So this is like a big bang point. Okay, as time becomes evolved. Later on, the AT would increase in a concave down way, and then after an inflection point, it becomes a concave up way. Okay, this is our current time here. Okay, current time we already observed that our universe is expanding with acceleration. Okay, so we have 3 scenarios. One is called the big crunch. Big crunch means our universe would go to 0 eventually, would be This would be bad, okay? And then big rip means infinite time the universe will be ripped off, okay? But the middle one is called the dark energy scenario. This is what to be expected, dark energy scenario. In this scenario, we are going to have the picture for the AT this way. A0, like we mentioned, A0 at time 0 is equal to 0, okay? The radius of the universe is 0. And then the universe would be expanding all the time so that you have this positive velocity for the expansion of the universe, okay? The first line of equation here is called the Big Bang scenario, okay? The second one is acceleration today or later, the acceleration would be positive, or even better, acceleration would follow, the AT would follow exponential law here, okay? AT would increase exponentially, okay, for large t. And then the E here has a name called dark energy, okay? Dark energy is something we don't know. We don't know the reason for E here to be present, okay? To make our universe to expand like exponential function, okay? Physicists consider something called quintessence. Quintessence, okay, because the Greek culture, in the Greek culture, people say that the universe is made of 4 elements. One is called air, the other one is called earth, the other one is called fire, and then water, okay? Quintessence is the 5th element, we don't know, okay? The physicists say, okay, quintessence is responsible for the expansion of the universe, for the expansion, for the dark energy, in fact, okay? So to try to use some notion called quintessence to explain the presence of dark energy, okay? So here is what people do. Mathematically, they introduce a scalar field, phi, Q here, called quintessence, okay, scalar field, real scalar field. And with potential energy and kinetic energy, okay? And then this is our Lagrangian, okay? And then we put in our equation, Einstein equation, and then solve the Einstein equation, see what this will give us, basically, okay? In this case, you can make this theory here, the Q quintessence, into a fluid, a cosmic fluid, so that your pressure of this quintessence is given by the Lagrangian, in fact, and then the density of matter is given by the energy density, Hamiltonian, okay? The ratio there is called the equation of state, okay? So that when the quintessence is 0, the potential is not 0. Then potential here is something called a cosmological constant, in fact, okay? So in this case, the W there is, the ratio is -1 in this case. So this is the old story about quintessence. Quintessence, what is our freedom of quintessence in order to get our desired dark energy evolution, this kind of thing? Obviously, you cannot change anything here. The kinetic energy is fixed. What you can change here is your potential energy, right? Your potential energy is, you can have freedom to choose your model, basically, okay? So this is people do here, okay? You can take your phi q to be in this kind of polynomial type, exponential, or this rational function type, okay? And then you can get desired cosmology or the evolution of the universe, for example, okay? People like, for example, if you look at this physicist called Andre Linde, he did this kind of pioneer work, okay? Quintessence. His work got this kind of a big prize called the breakthrough prize in physics. This was like 5 years ago he got this, okay? Due to his work in cosmology and quintessence, okay? What is relevant for us is called K-essence. K-essence means what? You are going to fix your potential function here, but make your kinetic energy K here flexible in the same idea of Born-Infeld, okay? In the old theory, in the quintessence, your kinetic energy was fixed, right? It's given by this 1/2 of Q dot squared. But here you're going to make it general, okay? fx here is general, x is 1 over phi dot squared, okay? Make this one flexible, but your potential here fixed, basically, and see what happens. Now, this one has a huge advantage, okay? Okay, by the way, the quintessence, the K here means kinetic. And kinetic part is free to do, okay? And from here, you can formulate your cosmic fluid pressure and the cosmic matter density here, okay? So that your equation of state, which is a relation between density and pressure, can be solved by linking the two equations together, okay? And in this way, you can discover your model of F here. F, what is F? F is your model here, Okay, your basically your Born-Infeld model, F, your nonlinear function here, can be discovered based on your given equation of state, okay? So in this way, you can discover your Born-Infeld theory or K theory, K-essence theory, as by solving this ODE here, okay? So here will be a few examples, okay? Let me go to this example here by the time limit, okay? In cosmology, some fluid called the Chaplygin fluid is famous, okay? In this case, people write the pressure here as a function of the density, but negative there. Why negative? Negative means this kind of law would be responsible for the expansion of the universe, because the pressure negative is like if you take an airplane, suddenly someone opens the window, for example, then the pressure in the airplane becomes negative, and then everything would be blown away, right? Okay, so that is responsible for the expansion, for the accelerated expansion of the universe. Okay, negative pressure would be responsible. But this is like a hypothetical fluid, okay? What is the physical meaning? What is the theoretical foundation for this Chaplygin fluid? Okay, it's not easy to explain, but you can look at this equation here. You solve this equation here, you can come up with your model, a Born-Infeld model, so that you can have this interpretation. You can solve for your equation to get your K-essence interpretation of this equation of state. Okay, so Chaplygin fluid has this kind of interpretation. Okay, in terms of Born-Infeld theory. Okay, and you can insert everything into the equation and solve, and then you can get this result. Our scalar factor would have this big bang scenario. A0 can be 0. A0 would be 0, and A would be increasing, okay, the scale factor. And then the A here would follow exponential law as t go to infinity, so that the quantity here would be recognized as your dark energy, okay? So that in the Chaplygin model there, you see clearly that the coefficient to the 1/4 in the power there becomes our dark energy in this case. Dark energy. This A here is dark energy. Okay. So let me make a summary quickly. The time is up. My time is up. Sorry. So today we studied the Born-Infeld theory, which is a nonlinear theory. The theory would accommodate both electric and magnetic charges of finite energies. Okay, but you can make a nonlinear extension of the theory so that the theory would be biased. Biased means it will only accommodate electric charge of electric point charge, but it will reject a magnetic point charge, so that the monopole problem is being resolved. Okay. Number 3 is finite energy of electric and magnetic charge enable us to regularize our black hole metric. Okay, so that we have reduced singularity or even removed singularity in the black hole metric. Okay, which is like an implication. Okay, or relegation of energy and the mass, this kind of relation, okay? So that our singularity due to the presence of electric and magnetic field will not be more than mass, okay? Same as mass, for example, okay? And then number 4, Born-Infeld theory can be applied to cosmology so that you can have you can achieve a field theoretical interpretation of some exotic fluid model, for example, the Chaplygin fluid model by field theory interpretation in terms of the Born-Infeld idea. And all this are based on nonlinear field theory, okay? Linear theory won't solve the problem, but nonlinear theory will, okay? So finally, let me recommend this review article, okay? It is about a Born-Infeld inspired modification of gravitation. This is a physics report 2 years ago. Okay, it's quite interesting to look at. Okay, thank you very much for your attention.
So thank you, Yisong. I'm going to clap.
Thank you very much.
And I've asked Chris to take over the Q&A moderation because I have a 4:30 appointment I have to run to.
I'm sorry, I run over time. Yeah, I'm sorry. Yeah, that was
okay.
Yeah.
Thank you for a great talk.
Thank you very much.
And with that, I'd like to ask if anybody has any questions that they'd like to have this take this opportunity to get answered. Please feel free to just speak up. If you don't want to, you could also try the chat, but definitely please do speak up.
Yeah. Can I ask? So you mentioned these new models, and the original motivation was like, okay, so I'm having issues with my regular kinetic energy, so I'm going to shift to this thing that matches with what my expectations are for relativity, and associated with that is like a new symmetry that you add to your Hamiltonian. So when you do a Born-Infeld model, are you keeping Lorentz symmetry, and are you also introducing any new ones?
All the symmetry will be there already. Okay, all this they have no issue there. Okay, you have this Lorentz symmetry. All this would be there. Okay, you keep everything here relativistic.
Right. Thank you.
Yeah.
So I was kind of
the thing is, yeah, because everything would be a function of your Lagrangian, your Maxwell Lagrangian. Maxwell Lagrangian is invariant. Remember, the S here is your Maxwell Lagrangian, right? Maxwell, okay? And then you consider your nonlinear theory to be in Fs in this way. This is invariant. So therefore, this is invariant.
Right, yeah, that makes sense. Okay, thank you.
Makes sense, right? Yeah. Okay, so it's powerful nonlinear extension.
Are there any other questions? I guess I have one, and I have to confess I'm really not very well versed in physics and relativity, but I was musing at the motivation for using the Lorentz transform and the electron model. I mean, it sort of makes sense, obviously, and when you're thinking about large scale structures and relativistic senses and you approach high speeds. But what was the inspiration to try to make that that adaptation to the model of an electron? In other words, I was hazy on the motivation for trying to extend relativistic arguments to the electron.
The motivation was to get finiteness of energy, or to introduce some cutoff, as you do in relativity or electric field.
I get that, but what was the inspiration? So in other words, that's a specific mathematical form, and maybe it could have been done in a different way. Why that form?
You mean, okay, why the radical form?
Yeah.
the radical form came from invariance. Okay, basically you look at how the special relativity was introduced, right? And then you talk about invariance, for example, proper time or this kind of discussion. Okay, if you want to make yourself your theory invariant under Lorentz transformation, then you introduce this kind of notion, like how you compute the proper time, this kind of, okay. And then you have this kind of radical thing to come in.
So you're saying that the invariance was portable across the two use cases, the two
Yeah.
seemingly very disparate.
Yeah,
You know, because the connection seems, you know, a big jump.
Yeah,
big jump.
right.
Yeah.
Right. You have no other choice, right?
I see.
Yeah, you have no other choice but the radical root formulation.
So this was more just more of like a Nether's theorem type motivation than an inspiration from relativity.
Yeah. You have this kind of like proper type, right? D like okay, ds squared equals to c squared squared. Oh, okay. So the t squared, and then minus minus dx. All the things together. Okay. dy squared, dz squared. I cannot write well here.
No, I get you. I get your idea.
Okay, basically, right. All this would be t, x, y, z. This are coordinate dependent.
I see.
But this won't be dependent. It's invariant. Okay. So therefore, it is meaningful to compute this ds here with the proper time here as an invariant. Okay. And if you do this, and then you would, if you count that one, you would have radical root coming.
Yeah.
You would have radical root.
I gotcha. Okay.
Yeah. Right.
Thank you very much.
Yeah.
I do know we're running a little bit late, so just one more quick check to see if there are any other questions before we thank our speaker for a great talk. Okay. Well, thank you so much again. That was really fantastic. Yeah. If anybody. Yeah, if anybody has any questions, maybe they could stay a few minutes after potentially, but otherwise, thank you again very much for your
Thank you very much.
talk.
I'll stay longer to see if anyone has questions.
Thank you so much.